What enzymes are involved in glycolysis? Have you ever wondered how your body generates energy during intense workouts? The process of glycolysis plays a key role in this energy production. Let's break down the enzymes involved in glycolysis and how they relate to strength and conditioning careers in sports. Glycolysis is the method by which glucose is broken down in the cell to produce adenosine triphosphate, which is essential for muscle contraction and performance. This process involves a series of chemical reactions, each facilitated by specific enzymes. Understanding these enzymes is vital for anyone pursuing a career in sports, particularly in strength and conditioning. First up is hexokinase. This enzyme kicks off glycolysis by adding a phosphate group to glucose, transforming it into glucose 6-phosphate. This step is important because it traps glucose inside the cell, making it available for energy production. Next, we have phosphoglucose isomerase. This enzyme converts glucose 6-phosphate into fructose 6-phosphate, setting the stage for the following steps. Then comes phosphofructokinase, often regarded as the most important regulatory enzyme in glycolysis. It adds a phosphate group to fructose 6-phosphate, creating fructose 16-bisphosphate. This step is crucial for controlling the speed of glycolysis. Following that is aldolase, which splits fructose 16-bisphosphate into two 3-carbon molecules, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. Then, triose phosphate isomerase converts dihydroxyacetone phosphate into glyceraldehyde 3-phosphate, allowing both molecules to continue through the next steps. Next, we encounter glyceraldehyde 3-phosphate dehydrogenase. This enzyme catalyzes a reaction that produces nicotinamide adenine dinucleotide hydrogen and adds a phosphate group to glyceraldehyde 3-phosphate, forming 13-bisphosphoglycerate. Phosphoglycerate kinase then transfers a phosphate group from 13-bisphosphoglycerate to adenosine diphosphate, resulting in adenosine triphosphate and 3-phosphoglycerate. After that, phosphoglycerate mutase rearranges the phosphate group on 3-phosphoglycerate to form 2-phosphoglycerate. Enolase comes next, removing a water molecule from 2-phosphoglycerate to create phosphoenol pyruvate. Finally, pyruvate kinase transfers a phosphate group from phosphoenol pyruvate to adenosine diphosphate, producing adenosine triphosphate and pyruvate. This marks the end of glycolysis. Each enzyme has a specific role in converting glucose into pyruvate and generating adenosine triphosphate. The regulation of these enzymes, particularly phosphofructokinase, allows the body to adjust energy production based on physical activity demands. For professionals in strength and conditioning, knowing about these enzymes helps explain how athletes generate energy during high-intensity exercise. For instance, when an athlete sprints or lifts weights, glycolysis becomes a primary source of quick energy. Understanding enzyme regulation can assist coaches and trainers in designing workouts that optimize energy use and recovery. Practical applications include monitoring training intensity to prevent over-reliance on glycolysis, which can lead to muscle fatigue and lactate buildup. Coaches can use this knowledge to plan rest intervals and nutrition strategies that support efficient energy production. By grasping the enzymes involved in glycolysis, professionals in strength and conditioning can better support athlete performance, recovery, and overall health. This knowledge forms a foundation for anyone working in sports, from coaches to trainers to sports scientists.